Hi, my name is Shaked Matar. I'm a PhD student at Ben Gurion University of the Negev, and I will present our work, Ultra-Sparse Near-Additive Emulators. This is a joint work with my advisor, Michael Elkin. So we have an unweighted, undirected graph, and this graph can obviously have many edges. And the computational complexity of many algorithms depends on the number of edges of the graph. And so we ask ourselves, can the graph be represented more concisely? And the answer to that is yes, if we care only about the distance matrix, meaning for every pair of vertices UV, we care about the length of the path between them, but we do not really care what is the actual path. So we know that we can construct for our graph, we can construct an emulator, which is a sparse graph on the same vertex set that has a distance matrix that it is relatively close to the original distance matrix. So formally, if we're given an unweighted, undirected graph G, a graph H on the same vertex set is 1 plus epsilon beta emulator for G if two conditions hold. First, we require that the distances in the new graph will not be shorter than the distances in the original graph. Second, we also ask that the distances in the new graph will be a good approximation for the distances in the original graph, meaning that we allow for 1 plus epsilon multiplicative error plus an additive of beta error. If H is a subgraph of G, we say that H is a 1 plus epsilon beta spanner for G. So our goal is obviously to achieve sparse emulators, and we want to have them as sparse as possible. Now, we know that we can take a spanning tree of the graph, and then we have something that is very, very sparse, but the relation between the distance matrix in the spanning tree and in the original graph is not very clear, and it doesn't provide us with a good approximation of the distances. So the question is, how sparse can we get? How close can we get to the spanning tree before we lose all meaning of stretch? So this question was asked a while ago, and Elkin and Peleg have shown back in 2001 that one can construct near-additive emulators with size order of log kappa times n to the power of 1 plus 1 over kappa, and have additive stretch of order of log kappa over epsilon to the power of log kappa minus 1. Torp and Zwick have also shown another construction of near-additive emulators, but these emulators are scale-free, meaning that these emulators provide 1 plus epsilon beta approximation for every epsilon that is greater than 0 simultaneously. Petty also devised a construction that further minimizes the size of the emulator, and Elkin and Neyman have also shown an efficient construction of sparse emulators. However, note that all of these constructions have size of at least 2n. So the question that we asked is, can we compute ultra-sparse emulators, meaning emulators of size n plus little o of n? So in the current paper, we have shown that one can construct ultra-sparse emulators with meaningful stretch. Specifically, we have shown that for every epsilon and kappa, there exists a beta, such that for every n-vertex graph, there exists a 1 plus beta emulator of size n to the power of 1 plus 1 over kappa with no leading constant. We've also devised a centralized construction that computes such emulators in polynomial time. We note that by setting kappa to be little omega of log n, the term n to the power of 1 plus 1 over kappa becomes just n plus little o of n. In other words, these emulators are ultra-sparse. We've also devised efficient distributed and centralized algorithms that build ultra-sparse emulators. Specifically, we've shown an algorithm that, given parameters epsilon and rho, constructs 1 plus epsilon beta emulator of size n plus little o of n. The running time of the algorithm is order of the number of edges times n to the power of rho in the centralized model, and order of beta times n to the power of rho in the distributed congest model. So I will explain our approach now. The algorithm was achieved by using the well-known superclustering and interconnection approach, which I'll explain shortly. In the current algorithm, we also introduced a new charging argument for the analysis of the size of the emulator. Basically, what that we have shown is that there are many vertices that are charged only with a single edge, and that there are only few vertices that are charged with many edges. In addition, in order to provide an efficient distributed algorithm in the congest model, we have devised a new procedure for the construction of superclusters. So I'll explain now the superclustering and interconnection approach. Our goal is essentially to connect vertices with other vertices in their vicinity. So here in the figure, I want to add all these yellow edges. Now, for vertices that do not have many neighbors, that's not a problem. I can just connect them with their neighbors and we're done. The problem is that some vertices are popular, meaning that they have too many other vertices in their vicinity that we want to connect with. So we need to deal with them somehow. What we do is that we form superclusters. So first, we identify all these popular vertices. I say that all these blue vertices are popular, and by that, I mean that I cannot just simply connect them with their neighbors. Then we form superclusters that cover these popular clusters. Now, we want to make sure that on the one hand, we cover all the popular clusters, and on the other hand, we want to minimize the number of superclusters that we form as well as their radius. When we're done with that, after we've covered all the popular clusters, we can safely interconnect the vertices that are not popular, or the vertices that are not covered, with other vertices in their vicinity, because we know that all the popular ones are covered and we're left only with the ones that are not popular. And then we repeat this process on the cluster graph. So to summarize, our algorithm works in phases. In every phase, while there are still popular clusters, we first cover the popular clusters with superclusters, and then we interconnect the remainder of the clusters. So how do we decide who is popular? We say that a cluster is popular in phase I if it has at least di, which is equal to n to the power of 2 to the power of I over kappa clusters within distance delta I from it, for an appropriate distance parameter delta I. This degree sequence was also used in previous papers that used the superclustering and interconnection approach, because it essentially enables one to claim that in each phase we contribute at most n to the power of 1 plus 1 over kappa edges. We show here that we can argue that each phase contributes much, much less. So the traditional analysis of algorithms that use the superclustering and interconnection approach follows these lines. So we analyze the contribution of each phase I, and we bound the number of the superclustering edges and the number of interconnection edges separately. We say that in each phase we add at most n-1 superclustering edges, because every vertex adds at most one superclustering edge to our emulator, and the center of the cluster never adds any superclustering edges. For the interconnection edges, we say that the number of interconnection edges is at most the number of clusters we started with times the degree parameter. And this analysis overall allows us to say that in every phase I, the number of edges that we add is upper bounded by order of the number of clusters times the degree parameter. Now, in the current paper, we introduced a new charging technique. Basically, we've made the following observations. So first, when a cluster adds interconnection edges, it leaves the game. By that, I mean that it will not add any superclustering edges in the future. It will not be counted as someone I need to connect another cluster with. It simply won't be taken into account in the future. Another observation is that each supercluster takes many clusters of this phase. Specifically, each supercluster that we form must contain at least di+1 clusters that are still in the game. Together, the two observations imply that there is a trade-off between the number of clusters that add interconnection edges and the number of superclusters that we form. As a result, we obtain the following tight analysis. So we say we mark by Ci the number of clusters that we started in phase I. And then we upper bound the number of clusters that add interconnection edges. So the number of clusters that add interconnection edges must be at most the number of clusters that, must be the number of clusters we started with minus the number of superclusters that we formed times the degree parameter +1. Because we know that every supercluster took with it at least di+1 clusters. Then we bound the number of superclustering edges. So we know that the vertices that add superclustering edges are the vertices that did not become centers of superclusters and did not add interconnection edges. So overall, the number of clusters that add superclustering edges is at most the number of clusters we started with minus the number of clusters that became cluster centers minus the number of clusters that add interconnection edges. When we sum the contribution of all phases together, we obtain the following term. Now, note that we have here di minus 1 to the power of 2. And recall that we set di to be equal to n to the power of 2 to the power of I over kappa, which means that this term just becomes 0 and this entire sum is cancelled, and we're only left with this C0 times D0. So to summarize, the overall size of the emulator is at most the number of clusters we started at the beginning, which is n, times the first degree parameter, which is n to the power of 1 over kappa. And so we obtain that the overall size is n to the power of 1 plus 1 over kappa with no leading constant. I'll briefly explain now how we modified the superclustering procedure to provide a distributed algorithm that is efficient. So first, I will briefly introduce the distributed congest model. Our network is represented by an n-vertex graph. The vertices communicate with one another in synchronous rounds. In every round, we allow each vertex to send messages of length at most order of log n across each edge. And we ignore internal computations. So the basic tasks of the distributed algorithm are the same as in the centralized version. Specifically, while there are still popular clusters, we form superclusters, and then we interconnect the unclustered cluster, the remainder of the clusters. Now, The interconnection step is relatively straightforward because we know that we're dealing with areas of the graph that are relatively sparse. They do not have many vertices that need to communicate with one another, and so we do not fear that congestion will occur. The problem is, how do we form superclusters? Because here we need to deliver messages in areas of the graph that are inherently very dense. And we know that they have at least some number of clusters, but we don't have an upper bound on the number of clusters that are in them. Specifically, our problem is that we want to form a supercluster and say that all these vertices want to join the supercluster that is formed around the blue center here. And so each one of them needs to send a message to the blue vertex and tell it that they add a superclustering edge to it. Now, because many vertices try to send a message to the blue vertex and each one of them wants to send a unique message, it's very possible that there will be some hub vertices that have a lot of congestion in them that need to deliver too many messages. So to solve this problem, because we just can't send all of these messages to the blue vertex, what we've done is that we essentially divide the supercluster into several large superclusters, very large superclusters, and one supercluster that may be relatively small. So to summarize, we've shown constructions of ultra-sparse emulators, and we've shown that ultra-sparse near-additive emulators do exist. And we've shown that they can be efficiently constructed both in the centralized model and in the distributed congest model. So thank you very much.